Hello, I'm Dave.
I'm Todd,
And I'm Hayden.
and this is Lab 8, the Wheatstone Bridge. Wheatstone bridges allow circuits to be made in order to find unknown resistor values. Kirchhoff's voltage and current laws are both major factors in finding the unknown resistor values. These two laws are applied by using the loop and junction methods, which breaks a circuit into sectional loops to find voltage and nodes to find current. The sectional loops allow voltage to be found because the voltage at node B and C are the same. From using the previously stated information, the unknown value for Rx is able to be found by using Kirchhoff's voltage law. It is possible to use Kirchhoff's current law because it is known that the current through path BB and BD should be equal.
So here's a diagram of the Wheatstone bridge that we used in this lab. And the whole foundation of this lab comes from understanding the potential difference between point A and point B is going to be the same as the power source. And the variable resistor, which in this case is R2, will be changed to the point where the current going through the center branch with the ammeter is going to be 0. And that is fundamental to proving our KCL and KVL, which we'll do in the next part. So first I'm going to prove KCL, which is Kirchhoff's current law, which basically states all current entering a node must be the same as the current exiting the node. This is a basic principle of conservation of energy. So I'm going to do node B first, keep it simple. And to do this, I basically have to see that my current's going to come up from the power source and enter point A. And knowing the current coming into point A, it's got to split off to these two branches going through Rx and R1. But since it's a Wheatstone bridge, we know the current coming through this branch is going to be 0. Therefore, if you look at the current coming in and out of node B, you got the current going through the unknown resistor Rx and going in, and then the current going through R2, which is our decade box, coming out. There's no current coming up through this, so it's not even in the equation. Therefore, you can get this equation right here where the current through the unknown resistor equals the current through the decade box, R2 in our case. Basically saying these are equal currents. So here's a redoing of the last diagram we had, and we already found that the current going through from A to B and B to D is going to be the same current, so I'm going to call it current 2. Same thing down here, current to A to C and C to D is going to be the same, calling that current 3. We're going to do loop equations here, which basically means I know the voltage from A to B has to be the same voltage from A to C, and likewise from B to D, the voltage is the same as from C to D across these resistors. So taking that equation of the voltage across our axle equal voltage across R1, I can sub in Ohm's law to get the resistance in the unknown resistor times the current 2, since it's up here, equals the resistance of this resistor down here times its current, which is current 3. Now I can rearrange that equation so the resistor's on one side, the current's on the other, and I'll get Rx over R1 equals current 3 over current 2. I'm going to keep that for later. Once I do the whole loop equation for the other side, just the same way, we get an answer that comes out to be resistor 2 over resistor 3 equals the current 3 over current 2. Now the important part here is that the currents that I got here, they're the same ratio. So I have current 3 over current 2, current 3 over current 2. Because it's the same thing, I could substitute these equations together. You get the equation that we used, which is Rx equals R1 times R2 divided by R3. I'm going to plug into our equation what our value that we got from the decade box that came out to be 5,656. And once you plug it in, you get 11,312, which is 0.16% off. For the propagated error, we took our partial derivative and we plug our values in to get 130 ohms. So we use an ammeter rather than a voltmeter because the voltmeter comes with an internal resistance, which when you get a measurement, will put a resistor in parallel with the system, and that'll mess up our calculations.
Now let's say we had a similar circuit as shown here. What would we do? Knowing that potential rise must equal a potential drop in a loop, and that the potential drop or the voltage is equal to the product of the resistance and the current at the element, we can write an equation for loop 1 in the diagram. At a resistor, there's always a potential drop, and at the battery, there is a potential rise if going from the negative terminal to the positive terminal. Let's start with the top resistor in loop 1 and go clockwise. There is a voltage drop in that resistor, which equals the resistance of 1 ohm times I1, an unknown current. Then going to the bottom resistor, the voltage drop there is 1 ohm times I1 minus I3, or the current through that resistor. Finally, going up to the battery or the power source, there is a potential rise, so it is written on the opposite side of the equation. The same steps are taken to create 2 more equations for current loop 3 and the current loop under loop 3. Solving the 3 equations, we get I1 equal to 6 amps, I2 of 5 amps, and I3 of -1 amps. I3's direction is opposite of the previous assumption. Knowing the current in these three, we find all the currents through each resistor and the total current to be 11 amps. Since the voltage of the circuit is 13 volts, we find the equivalent resistance of the circuit to be 1.18 ohms.
Taking this equation up here to find the charge on a capacitor over a period of time, I plugged in all our values, solved for C, 8 seconds because we had the voltage there, and solving for the capacitor, we get 146 microfarads. We come over here to solve for current, plug our capacitor in to the charge divided by the time constant, and so on, get your value, 9.15 times 10 to the negative 5 amps.
By using Kirchhoff's loop and junction methods, it was possible to find the values for the unknown resistors. The percent difference involved did not exceed 7%, and the propagated error was highest at 1100 ohms, thus supporting the experiment and apparatus was sufficient.